Welcome back. So, in today's video lecture, we will look at the topic that involve intermolecular forces, right? So, we will look at various types of forces. We list the various types of forces, and after that, we will look at the some of the power law being used from the context of intermolecular or interaction pair potential. Okay, and after that we can look at the Leonard-Jones potential, Me potential. Leonard-Jones potential is the a special case of Me potential. We will look at the minimum potential, right, based on the Leonard-Jones pair potential, right. So we will begin our lecture. Let's begin. Yeah, so as we have just described, we will look at different types of forces. Remember, when we dealt with some lecture in module 3, sorry, module 2, we described some of these forces, right, using some schematics, right. For example, we talked about van der Waals forces of attraction. Uh, in that, we looked at the induced dipole, permanent dipole based on few molecule type and permanent dipole, right. So this comes from the polarity and asymmetrical shape. I mean the molecule which has the asymmetry, right, either due to polarity or due to the molecular structure. Okay, uh, and the London dispersion force. So these three forces come under uh, the umbrella called van der Waals force, right. So this is a physical force. Okay, van der Waals force refers to the attractive force, right, which is very short range. Okay, and between molecules. It is applicable between noble gas atoms or any non-polar molecules, right. Okay. So at least we have got about three forces under van der Waals forces, which is nothing but London or dispersion. So London force or dispersion force, which are often interchangeably used. Okay, this force, London or dispersion force, is always there, no matter whether we deal with neutral atom or charged system. So this van der Waals force always exists. Okay, it is because of the fluctuation in the electron, right, electron cloud. So due to which there will always be interactions. I mean attraction between the atom or molecules, right. So important point to be noted is this is not same as the covalent bond or ionic bond that we often talk about. Uh, in fact, this is weaker than covalent or ionic bond, right? So there's no reaction involved. These are physical forces, right? Yeah. So apart from van der Waals forces, we also have electrostatic force. So we also will also be dealing with electrostatic force. So as the name suggests, this electrostatic force comes from the it is a manifestation of Coulombic interaction, right. So let's say if you have got 2 point charge, let's say you have about 2 point charge, and if they are equal in magnitude, okay, you can say either they can be equal in magnitude or they may be different in magnitude, right, as well as the charge, right. It can be positive charge also, it can be negative charge also, but we are talking about 2 point charges, right, kept apart a distance, right, which is nothing but r. Okay, so in such case we know what is known as the Coulombic law, which says that it is proportional to product of 2 point charges, right. Okay, are inversely proportional to square of inversely proportional to r power 6, right. Yeah, or square of the distance, correct. Yeah. right? So q1 by q2 r square, right? So we know that from the Coulombic interaction, Coulomb's law, we know it is q1 q2 by r square, right? It depends on the distance as well. It depends on the magnitude of the charge as well. Okay, so that we know. And we talk about the steric force, which is also force due to a steric hindrance, right? So let's say we talk about, let's say we have the we deal with particle system. Let's say you have a sphere, okay, and sometimes the sphere can be grafted using some polymer, right. This can be polymer brushes, so you can expect some sort of polymer brushes on the surface. Now when another sphere of particle, right, uh, interacts, right, so like you have polymer brushes on top of this, okay. Remember, when this two polymer, particle grafted with polymer, when they approach each other, they cannot approach, very close to each other, because there will be a hindrance between the polymer brush. So this polymer overlap will be there. So when overlap between two molecules, polymer molecules take place, there will be a steric hindrance. So because of which they will not be able to penetrate further. Okay. On the other hand, there is something called depletion attraction, which is purely because of the osmotic imbalance. Say, so let's say no two particle will have symmetrical distribution of the polymer density, right? So in such case, you will expect that there will be imbalance in the what you call osmotic. There will be osmotic imbalance, which will push the particle, right, uh, towards each other, right? Because of which there can be depletion attraction. So there can be two different type of forces. One is the steric repulsion because of the steric hindrance. The other one is depletion attraction. That is because of the force due to osmotic imbalance, because we know that no two particle system will have symmetrical distribution of polymer brushes on the surface. So you might expect depletion attraction. So we will see them um, maybe one by one in detail sometime. I mean, in detail as we move along, right? Yeah. Yeah. So next we will look at the phenomenological theories, various theories, power law theories, right? Um, so the first successful phenomenological theory was proposed by van der Waals, right? Who is a Dutch physicist, right? Uh, who has contributed to these attractive forces between molecules. Okay, uh, so in the 18th century, right? And so this form of equation, very famous equation. This is van der Waals equation of state for real gas. So this was the first theory uh, that came into existence when for predicting the PVT relations of real gas, right? So it was modified from the ideal gas law, right? And in this equation, two aspects was covered. One is the attractive force between molecules, and another one is the excluded volume concept, right? So the attractive force between molecules was first proposed by van der Waals equation, van der Waals, in his equation of state, right? After that came me potential theory, interaction pair potential theory. This was actually modified, empirical, interaction pair potential. So this uses compact. This was proposed in a very compact form. You can see there are two terms, right? One is the attractive term. I'm sorry. This is attractive term. So attractive force is often denoted using the convention, negative convention, right? Whereas repulsive force is often described using positive sign convention, right? So here you have the negative force as well as positive repulsive force, and the constant, which is B and A. This is nothing but the strength of attraction as well as strength of repulsion, right? Okay, and you can see this exponent, which is n and m. Okay, m takes very large values, whereas n is very exponent of n is very small. Uh, so so this form of equation just came after the in the form of me interaction pair potential theory, but this was not very useful. Later, 1924, Leonard Johns actually proposed a special case of me potential. Here, he has used explicitly the exponent for attractive term and repulsive term. So, you can see this is coming from the attractive term, because attractive term, if you look at in the van der Waals equation, it is volume dependent, right? So, V is uh, you know uh, equal to r cube, right? So, since V square term was used in attractive term, the volume dependent term is can be also expressed in the form of a distance dependent, that is r power 6 term, right? Okay. So, which because V square is now converted into distance dependent term, which is r power 6, right? So, this comes from the molecular theory of van der Waals attractive force, whereas this one comes from the this does not have any molecular origin. Why the exponent of 12 was chosen, there is no specific reason to it, but the simplest the accepted reason is this is very easy to compute, right? If you want to compute, using, I mean, computationally, because r power 12 is easy to express, which is just the square of the attractive term. Otherwise, the exponent of m can be as large as possible. Okay, so this actually indicates that the repulsive force goes something like this, which is very steep, right? So this is something like your hot sphere potential, right? So here r power m can be any number as large as possible, right? But this r power 12 was just used to make it easier, to calculate the potential computationally, right? Okay, yeah. So this is the about the Leonard Johns potential. Okay, so minus b power r power 6 is basically attractive term. A power r power 12 is basically a repulsive term. Now we know the combined effect of van der Waals attraction and repulsion at the molecular level. So if you plot the potential versus distance, okay, as a function of distance or center to center distance between molecules, you can see that the repulsion force, the repulsive force as such, is going steeper, right, after some point, right? So this is going steeper because of this mathematical, you know, the uh, uh, the power law which we have used as x power minus 12. This the repulsive the yeah, so it reflects in this fashion, right? The repulsive force reflects in this fashion, whereas the attractive force is nothing but the long range, interactive force, right? And this part is nothing but your attractive strength, okay, right? So this represents the minima, right? It passes through minima. Okay, van der Waals force, which is a very long range force in this case compared to the repulsive force. Okay, so we know that the sum total of the attraction plus repulsion, if you plot on the same graph, you will see this the solid line is nothing but this total force, which is sum total of attractive force as well as repulsive force, and the dotted line is the repulsion force alone in this case, or attractive force alone in this case, right? Yeah. So now we can look at how to understand the minimum potential or minimum coordinates, right? So we know the pi, what we have referred to is nothing but b power r power 6, b by r power 6 minus b by r power 6 plus a by r power 12. Remember this b, the we want to denote this parameter b because it comes from the beta, which we will see later. This beta is nothing but the combination of d by, right, plus key sum plus London constant, okay, which we will see later, okay. So this is very easy to connect beta with b. That's why we often use this you know b in this, I mean, we use this notion b, okay. Right, now we know that from calculus, if you differentiate this potential with respect to r, right, because distance, and set that to 0, you would be able to get what is known as minimum radius, I mean minimum distance, right? So which we will see now. Now let's say if I differentiate this with respect to r and set it to 0, what will happen? Let's look at that. So d pi by dr will be simply nothing but minus 6, okay, into, right, minus b into r power minus 7, okay, and you will also have here plus uh, r power, sorry, plus minus 12 into a power r power minus 13. So since this is 0, you will have simply yeah, 12a into r power minus 13, and you will have simply 6 into b into r power minus 7. This you can cancel 2 times. So you will have 2a 2a into r power minus 13 equal to b into r power minus 7, right? So we would simply want what is known as r minimum, right? So you can bring this one here, which means this will be sorry, you can bring this over there, which means this will be r power 1 by 6, right? If I bring this over here, this will be uh, r power 1 by 6, right? This will be r power 6, yeah, r power 6, which is nothing but 2a by b, okay. So r is nothing but, so this is actually minimum, right? Because we have we determine this when by setting d pi by r equal to 0. So in such case, what we get will be a minima, which is nothing but Rm is nothing but 2a by b power 1 by 6, okay. So this is what we know, and since we know Rm, we can also evaluate what is pi m in this case. So pi m will be, we just have to substitute this over there. So we know what is pi m, so minus b into Rm power minus 6, okay, plus a into Rm power minus 12. So this is what we have. So we just simply substitute this pi m, I mean Rm, which is nothing but minus b into, we have Rm is nothing but 2a by b power 2a by power 1 by 6 whole power minus 6 plus a into, we have 2a by b, okay, which is 1 by 6 and whole power minus 12, right? So if you express this, this will be what? Minus 1, right? So this will be minus 2 in such case we can express this as, so we have minus b into right, so 2a power minus 1 divided by b power minus 1, right? Okay, yeah. Plus we have yeah, so a into, okay, so this will be 1 by 2 power 2 into 1 by a square into, okay, 1 by or yeah, b square, right? Okay, yeah. So here, yeah, so we have minus b square by 2a plus b square by 4a. So we have 4a common. Then we will have minus 2b square plus b square. So which will be minus b squared by 4a. So we know that the pi m evaluated at xm is nothing but minus b square by 4a, right? Okay, so what does it represent is, if you look at our equation, so this part is nothing but your xm and this part is nothing but your pi m, right? Okay, so this is the minimum potential and minimum coordinate, right? So here we will do some exercise so that we will be able to understand the interactive energy, right? You will be able to relate quite well. So let's talk about methane molecule. Let's say we have two methane molecules. They are approaching with each other, right? Okay, very closely with each other. Then you know that as they move very closely with each other, they will be, there will be van der Waals, right? Attractive energy. They will experience van der Waals force and then repulsive force, right? So now we want to understand, what is the, minima, right? When they, what is the minimum coordinate when they pass through the minima, that is total energy, which is sum total of van der Waals and attractive and repulsive energy, right? So that's exactly what we are going to now look at. As you can see, as soon as it crosses this. The energy goes into repulsive domain, you can see that they move very steeply, they grow very steeply. That's because as soon as they were, so that indicates that as soon as they cross that distance, right? So due to Pauli's exclusion principle, right? Because there can be electron cloud cannot overlap with each other. So this the infinite, because this repulsion energy is not finite, it indicates that the molecules cannot penetrate further. So that is exactly what it indicates, right? So the value, the repulsive energy cannot be finite value, right? It's infinity because it tells us that molecules cannot penetrate further, any further, right? So you can understand further by calculating what is the xm, the minimum coordinate, right? At which it will experience minima, right? It will pass through minima. So this you can calculate. We know that it is nothing but 2a by b, right, to the power 1 by 6. So this is nothing but, if you substitute these values, so remember the value, the a and b as units. In the case of a, it is joule meter per 12. In the case of b, it is joule meter per 6. So if you substitute these values, you will get my 0.42 nanometer, right? Right. So that is the minimum distance, the minimum coordinate for this case, especially when we deal with molecule that is methane. The pi m corresponds to this is nothing but 2.1 10 power minus 21 joule, right? Remember this pi here is expressed in the unit called joule, right, which is energy. So it is nothing but interactive energy itself. So if you want to understand or appreciate this number, what is the how will you relate? So you can relate this number with what is known as KBT, right, which is thermal energy. So we know that there is something called KBT, right? Boltzmann constant multiplied by temperature gives you thermal energy, right? This is nothing but thermal energy. So when you divide this number with the thermal energy, which is KBT, right? KB is nothing but 1.38 10 power minus 23, right? Joule per Kelvin. So when you into temperature, right? Multiply by temperature, right? If you do that, you will get this quantity, dimensionless quantity, right? So you can say that you can relate in this way. You can relate this pi m with KBT, right? Uh, let's say this is nothing but if I divide this with the KBT, I get 154 times KBT. So this pi m potential, minimum energy, interactive energy is nothing but it is actually at least 154 times KBT, right? So this in this way you can understand what is their strength, right? What is the strength of energy? So the strength of energy in this case is 154 times the thermal energy, which is nothing but KBT, right? So, so this will help you to quickly relate about the Leonard-John interactive energy, right, that we talked about, right? We will stop here. We will continue from the next lecture. Thank you.